Hello everyone, my name is Martin Hendry and I would like to thank the organisers for their invitation to speak in this session, in which I'm going to discuss how modern astrophysics content has been successfully embedded in the high school physics curriculum in Scotland. First, a word about me. I'm Professor of Gravitational Astrophysics and Cosmology at the University of Glasgow and a senior member of the LIGO Scientific Collaboration, for which I have chaired the LSC's Communications and Education Division since 2017. I was recently appointed Vice Principal and Clerk of Senate at my university, having previously been Head of the School of Physics and Astronomy from 2012 to 2020. In today's presentation, however, I'm mainly wearing some other hats. I currently chair the Learned Societies Group in Scotland, which advocates to government, industry and other stakeholders on issues affecting STEM education at primary, secondary and tertiary levels. One of the LSG's founding members is the Institute of Physics in Scotland, and I'm a former chair of the IOP Scotland National Committee and its Education Committee. In addition, for more than 10 years, I've worked closely with the Scottish Qualifications Authority and Education Scotland on developing and reviewing the high school physics curriculum and how it's assessed. And it's really that work which forms the basis of what I'm presenting today. I should note, however, that I'm speaking in a personal capacity and not formally representing any of these organisations. Now, this session poses the question, astronomy in schools, how do you get your administration and ministry to listen? Well, I'm pleased to say that in Scotland, the authorities were already listening, and the initiative to update the high school physics courses with more astrophysics content really came from the very highest level in government. So in my talk, I want to highlight how those curriculum developments have unfolded and what lessons we might learn for how embedding astrophysics content can best be achieved. So let me say a few words about Scottish STEM history next. There are some giants of the past to draw upon here, of course, including Lord Kelvin and James Watt. Glasgow University has the unique distinction of not just one, but two alumni with SI units named after them. And then, of course, there's James Clerk Maxwell, whose contributions to physics rival even Newton and Einstein. Perhaps more importantly, however, these scientists and their counterparts in other STEM fields embody a historical legacy of esteem for science and engineering, and in particular science and engineering education in Scotland, that still underpins our national education system today. Now, the origins of the curriculum developments that I'm going to describe go back to the late 2000s and are linked to, among several other factors, the 2009 PISA report, which saw the UK, and in particular Scotland, achieve only average scores for reading, maths and science. So this trend in the PISA results fueled the Scottish Government's drive to propose an ambitious reform of preschool, primary and secondary education, entitled the Curriculum for Excellence, that aimed to provide a more coherent, flexible curriculum. The CFE, for short, sought to develop student skills and knowledge in a holistic way, with much less focus on rote learning, and to build in our young people the four generic capacities shown on this slide in bold. The CFEs resulted in some top-level changes to the structure of school education in Scotland. Specifically, there are now 3 years of the so-called broad general education phase at the start of high school, where students are introduced to general science before a second 3-year period in which students undertake a series of national qualifications. Those are overseen by the Scottish Qualifications Authority, and they're known as the National 5, the Higher and the Advanced Higher, respectively. Now, most Scottish universities base their entry qualifications on higher results, but a large number of students nonetheless stay on at high school for a 6th year and study advanced hires, or perhaps expand their repertoire of hires. And I would say that from a teacher perspective, the CFE has also further strengthened the expectations for teachers to undertake continuous professional development, and has sought to further emphasise the importance of teachers engaging in practical work across the STEM qualifications, which I'm sure is something Lord Kelvin would have approved of. Now, some of that emphasis on building generic science skills can be seen in the so-called experiences and outcomes for CFE science, which are the key building blocks around which the curriculum is constructed. The bullet points are probably too small to read on this slide, but I've picked out some keywords below, and the crucial common theme is one of open-ended inquiry and critical thinking skills, with a focus on the scientific method. So not so much on what we know about STEM subjects, but how we have come to acquire this knowledge. Now, I should note that not everything has gone smoothly with how the CFE has been implemented. The OECD were recently commissioned to undertake a review of its implementation, and the OECD report made a series of recommendations, prompting a response from the Scottish Government that was published in 2012. And that response has in turn triggered a review, which is currently underway, of how the national qualifications and assessment are managed. I should stress, however, that the OECD report praised the general principles of the CFE, and its recommendations were mainly focused on how the overall implementation is structured and governed, rather than the specifics of the syllabus changes that have already been introduced. So let me next briefly describe some of those syllabus changes, and I'll focus on the higher and advanced higher physics courses. As I've summarised here, the changes have been designed to promote a deeper understanding of the physics, developing critical and open-ended thinking skills, and ensuring that students gain an appreciation of current research. And the fact that Scottish researchers have been deeply involved in recent exciting developments like the Higgs boson detection, the discovery of gravitational waves, and the launch of GWST, well, that has certainly helped with that. There are 4 units in the higher course. The first, in Our Dynamic Universe. In that one, the students are introduced to the basic concepts of special relativity, including time dilation and length contraction, deriving the relevant formulae from first principles. Our Dynamic Universe also covers basic cosmology, including the Hubble expansion, the evidence for a hot Big Bang, and the current paradigm of dark matter and dark energy in an accelerating universe. Although the latter concepts are presented and discussed primarily as a means to illustrate how we develop and then test cosmological models, rather than as a definitive and entirely settled theoretical consensus. In this way, we're also hopefully building students' understanding of how science works and evolves as competing hypotheses are investigated. In a similar vein, the Particles and Waves unit introduces students qualitatively to the basic principles of the standard model of particle physics, but emphasises not just how far we have come, but also where the remaining gaps in our understanding lie. The Particles and Waves unit also introduces the key ideas of wave-particle duality, focusing on the photoelectric effect, the double-slit experiment, and its implications for a quantum description of reality. And then finally, in addition to the unit on electricity, which was streamlined somewhat from its earlier form, the CFE Higher also introduced a new Researching Physics unit, in which students undertake a short piece of research on a topical subject of their choice. Popular subjects that schools have chosen include, for example, exoplanets, where students learn about exoplanet detection methods and explore real data from sources such as transit light curves. To test a simple hypothesis, for example, how the data depends on particular physical variables like the radius of the planet. Moving on to the Advanced Higher, this contains a unit on rotational motion and astrophysics that includes a significant amount of new content, for example, introducing the key ideas of general relativity via the equivalence principle. Although the GR section doesn't include any complicated maths beyond understanding Pythagoras, it does cover a basic qualitative discussion of the geometry of curved space-time, and students are introduced to the Schwarzschild radius and the event horizon. This unit also includes a basic description of the life cycles of stars and the Hertzsprung-Russell diagram, building on the concept of black body radiation that's already been covered in the higher course. Then next, in Quanta and Waves, more basic quantum physics is introduced, including the Bohr atom and the concept of the de Broglie wavelength. And finally, in Electricity and Magnetism, students are familiarised with the idea of EM waves and how the speed of light connects to the permittivity and permeability of the vacuum, as well as the broader significance of James Clerk Maxwell's work as an example of unification. So in the final part of my talk, I will now briefly consider what are the key lessons we have learned in Scotland over the past decade, as these changes to the higher and advanced higher courses have bedded in. I guess the first point to note is that, as was anticipated by the qualifications design teams, the new astrophysics material has taken many teachers quite far from their comfort zone, either because they graduated without having covered these topics at all, or indeed they graduated before these ideas, like the accelerating universe, for example, were even known. Compounding this issue of the newness of the material was the fact that, despite the overall reform in Scotland being referred to as the curriculum for excellence, the new physics courses had neither a rigidly defined curriculum nor, at least initially, an approved textbook, although within a few years textbooks had been written for both the higher and advanced higher, as shown here. Instead, teachers were provided with a set of experiences and outcomes, as we mentioned before, outlining the content that their students would be expected to understand. Developing the course materials to support these experiences and outcomes relied heavily on the work of early adopter schools who introduced the new courses several years before they were rolled out across the entire country. So here's an example of the content tables provided by the Scottish Qualifications Authority for the introductory special relativity content, which were designed to give teachers guidance on what they should cover and suggestions on how they might do this. Now, this flexibility which teachers were given to develop the curriculum was understandably somewhat daunting for many, but at the same time has encouraged a great deal of cooperation and collegiality in how resources have been created and shared across schools and local education authorities. At first, admittedly, there was something of a Wild West flavour, with even neighbouring schools sometimes adopting different approaches to how the course was taught. But this quickly gave way to an impressive degree of self-organisation, with a few different stakeholders acting as sheriffs to support this. And of course, the textbooks now also help to guide teachers while still not imposing too rigid and uniform an approach. Now, one of the prime movers in all that support has been the Institute of Physics in Scotland, acting consistently with the IOP's UK-wide education strategy for supporting teachers, but tuning the support in Scotland to the specific needs of the CFE. For example, as reported recently in Teachers Resource magazine, as shown here, the IOP Scotland team has taken over the task of curating the excellent Guzzled site. This is a teacher-led initiative to organise and share CFE physics teaching resources. Guzzled was itself developed from an earlier online resource sharing hub created by the teachers, known as the Scottish Physics Teaching Resources, or SPTR.net, but almost universally referred to colloquially and affectionately by the teaching community as the Magic Physics Pixies. The involvement of the IOP Scotland now helps to ensure a degree of consistency and quality control in the resources that are shared, but it is still fundamentally a community-led approach. Here's an example on how we define the parsec as a distance unit from the Our Dynamic Universe course notes developed and shared by teachers at Mearns Castle High School, close to Glasgow. It really would not look at all out of place in my first year university Introduction to Cosmology course. Now, another piece of critical teacher support that IOP Scotland provides is an online physics discussion forum called Sputnik. This has been a great success and has gone on to spawn equivalent forums for chemistry and biology. And it's subscribed to by a significant fraction of all the physics teachers in Scotland. Again, the text here is probably a bit too small to read, but these are just a snapshot of the teacher responses over a couple of days in mid-October, when I should also note many teachers were actually on their mid-term vacation. And they were responding to a question from one teacher about world lines on space-time diagrams. The quality of the discussion on the forum is really excellent, with threads about everything from the deeper meaning of the physics and links to current research, to useful analogies and practical tips on how to present complex physics ideas in a classroom setting. And that focus on deeper understanding is especially pleasing to see in the teachers' discussions, but it's also firmly hardwired into how the students are assessed via the national qualifications. Both the higher and the advanced higher exams contain short, open-ended questions that encourage students to reflect upon and discuss situations based on the physics that they know. These questions have quite often focused on the concepts that underpin the new astrophysics content, as can be seen in these examples from the early years of the new courses about 10 years ago. They explore ideas about gravity, the equivalence principle, and then the other question, even the brief flurry of publicity about the OPERA experiment seemingly faster than light neutrinos. And then here in turn is an open-ended question from the most recent Advanced Higher National Exam in 2022. The content about stellar luminosity and distances could have been asked via more conventional linear type questions, but instead the students are asked to reflect upon a series of statements and respond to them using their understanding of stellar astrophysics. Now, feedback from students and teachers about these types of open-ended questions is generally supportive, although they have taken a bit of getting used to. Of course, given the financial constraints under which schools often have to operate, maintaining significant experimental input in the senior phase courses can be a challenge too. But making sure this is a priority has been an important goal of the CFE. The main points to note here are to sing the praises of external bodies such as the Scottish Schools Education Research Centre, or SERC, which provides physics teachers with guidance and advice on better approaches to experimental methodology, including demystifying the treatment of errors and uncertainties, and helping them to share good practice on innovative ways to perform advanced experiments using everyday household equipment. The IOP's also done an excellent job here and has collated thousands of videos and guidance materials on how to get the best out of physics experimental work via their IOP Spark website. A really good example of the kinds of teacher-led innovation that has worked very well here can be found in the Higher Researching Physics unit. SERC and IOP Scotland worked with the SQA and researchers from the universities to develop guidance notes on some exemplar projects, including one on exoplanets as shown here, that describes how to simulate transit observations using a lamp and simple open access graphing software that can be run on students' mobile phones. So here are some students in Portree High School when I visited them on the island of Skye, showing off their cheap but highly effective kit, which they built and tested all for themselves. So finally, I hope it's very clear from all these lessons learned that the support provided for teachers' continuous professional development from organisations like IOP Scotland and SERC has been absolutely vital. Infrastructure like Sputnik has enabled the teachers to quickly and easily share best practice with each other and to learn from others' mistakes. And the universities have a significant role to play too, both via individual students and staff interacting with teachers in their local networks, or via Sputnik, and through higher level coordination of support materials as has been carried out by the Scottish Universities Physics Alliance. Now, SUPA is a research pool of all the physics and/or astronomy departments across the country. It was established nearly 20 years ago. And although it's mainly focused on fostering research collaboration, it recently formed SUPA Education, which emphasises that the universities understand the importance of building strong and sustained links with the physics teaching community. The university community has also worked closely with, for example, Education Scotland to create multimedia resources that set the new higher and advanced higher courses in the context of current research. And myself and other astronomer colleagues have also contributed regularly to online or in-person GLOW meets. These are extended workshops and Q&A sessions with teachers hosted by Education Scotland, as well as online sessions that are live streamed on the SERC YouTube channel. This kind of online support infrastructure reflects the challenging geography of Scotland, with many teachers in the Highlands or Islands far away from the nearest city, never mind the nearest university physics department. However, the focus on extensive online provision did also allow our teacher support to adapt quite well to the pandemic, with excellent opportunities for regular, informal teacher CPD offered online by IOP Scotland over the past 2 years, for example, through its Talk Physics programme. There's still clearly merit in face-to-face contact too, however, and I'm very pleased that in 2022, IOP Scotland was able to resume its flagship Stirling Physics meeting, which often attracts several hundred teachers to in-person talks, workshops, and informal discussions. It's this kind of comprehensive community support that has helped to make the new higher and advanced higher courses such a success. So to conclude, after about 10 years, I believe that the astrophysics content in the CFE Physics Senior Phase courses has bedded in very well, no doubt aided by the spectacular physics discoveries that have unfolded in Scotland during this time, but certainly also helped by the wide range of CPD support that has been put in place by a range of different stakeholders. So if you still have to convince your ministry to introduce astronomy content into high school courses, then I would say the main lessons from Scotland are to make full use of the political and economic arguments that demand more STEM engagement to address significant employment gaps that are looming, to exploit the proven popularity of astronomy content and the way in which it builds broader STEM skills that will be needed to plug those employment gaps, and most of all, to lay the groundwork by ensuring you have the kind of teacher support from your universities and professional bodies that will make the courses a success. Thank you very much.